Thank you for the invitation. Thank you for the invitation. The topic of our joint work, an uncountable family of generalized inverse limit spaces homeomorphic to the German dendrite G3. It's a joint work with my student Sherzad Farhan. Thank you for the invitation. The abstract of my topic is we found uncountable family of inverse sequence whose inverse limit spaces are homeomorphic to the German dendrite G3. The factor spaces of each inverse sequences are interval and bonding functions are upper semi-continuous map, set value map. So there are uncountably many non-homeomorphic graphs in the family for bonding functions. In addition, we explain how finitely or infinitely many ramification points of order 4 may be added to the inverse limit spaces by modifying bonding function. As a general background definition, we have definition of hyperspaces. If X be a topological space, we define the following hyperspaces be the set of all non-empty closed compact subspaces. The set C of X be an element in the hyperspace, a connected element in the hyperspaces we denoted by C of X. We mean by a continuum non-empty compact connect matrix space housed of distance between two elements in or between two housed or between two hyperspaces as follows: be the infimum of each epsilon greater than 0 when A belongs to the neighborhood of B with radius epsilon and B is in the neighborhood of A around epsilon. We have definition of upper semi-continuous. I'm sure all of you are familiar with this. We say that a function from X to the closed subset in Y, an upper semi-continuous at the point X, if for each open set in Y contains f of X, there exists an open set U in the domain contain X such that for any T in U, f of T in is a subset of V. If an upper semi-continuous function, if a function be an upper semi-continuous function at all X, we say that f is an upper semi-continuous function. So when we have both of X and Y are compact matrix spaces, if in upper semi-continuous from X to the set of closed subset of Y, if and only if the graph of F is closed in the product of X cross Y. Inverse limit definition here. If we have a sequence of continua for each I, if I from xi plus 1 to xi be a mapping, the inverse limit is denoted by backward limit xi fi and defined as follows: the set of all xy I from 1 to infinity, xi equal to fi xi plus 1. Generalized inverse limit, we have if we have a sequence of continua and if n be an upper semi-continuous function, we define generalized inverse limit space as follows. We have when xn belongs to fn of xn plus 1 for each n. A metric on a hyperspace, we mean by such metric d of xy equal to the summation of xn minus yn over 2 to power n. We have more definitions here. Let's recall that a dendrite is a locally connected continuum with no simple closed curve. A subcontinuum of a dendrite is a dendrite and are hereditary unicoherent. A point P in a dendrite T is an endpoint if P complement is connected and we say it's an ordinary point if P complement has exactly two components, and we say that P is a ramification point if P complement has exactly two components, and we say that P is a ramification point So, in our work, we use some theorems frequently. That's why I like to at least read it here. We have this theorem we published before. If for each I from 1 to if I be an upper semi-continuous function, and all of factor space xi are dendrite, and all of graph of f of I are locally connected continuum, and for each t in xi, if I plus one inverse of t is a connected, then inverse limit is a locally connected continuum. And we need this theorem as well. When xi be a sequence of finite dimensional continua with trivial shape, and if I be an upper semi-continuous function such that the pre-image of xn is a continuum with trivial shape, then inverse limit is a trivial shape. Actually, this theorem is an analog of another theorem by Dr. Heretonic and Robert Rowe, because they proved earlier that if for all xn, if for all f xn, sorry, this fn plus one. Okay, if n xn be a continuum, and we prove it if n inverse be a continuum, we still get a trivial shape inverse limit. We need this theorem as well. If I be an upper semi-continuous function, and for each positive integer I, sorry, we don't need this. I changed this theorem. And suppose that the dimension of Gm prime is less than or equal to m, then the dimension of inverse limit is less than or equal to m. So yeah, no, it is okay for each I, for each positive integer I. This I go back to fi. So if this has happened, we say that inverse limit, the dimension of inverse limit is less than or equal to m. Recall that one-dimensional trivial shape locally connected continua are dendrites. Before we start our first main theorem, Ingram, in one of his paper, he proved that the inverse limit of a sequence of upper semi-continuous function having the graph of fi like this, then it is inverse limit is a German dendrite. And we proved this guy is also German dendrite G3. People before like to work on homeomorphic between inverse limit spaces like Banach when Markov interval have the same pattern, and n-type like Smith-Varagona and others. So here, our main theorem, we prove that we have uncountably many sequence of upper semi-continuous functions have the same inverse limit homeomorphic to the German dendrite G3. Before this, we need some notation and definitions to define our Ponti map. Let A and B be a finite sequence be a finite subset of 0, 1, and A intersection B be empty, and C be a set of 0, 1, because this C in the third theorem and others will be changed. And for each A in 0, 1, such that A not be in the union of this guy. Given A and B and small a, we define an upper semi-continuous function as follows. F of x be A union C when x is in the closed and open interval 0, 1. And when x is A, we have the full 0, 1, and f of x be equal to B union C when x be in the open close 0, 1. Let F be a family of all such upper semi-continuous function. For all AU be a finite set. If this has happened, any function satisfy this requirement, we see there is an element of this guy. The main theorem of this article is as follows. If F be in this family, then inverse limit is homeomorphic to the German dendrite G3. I like to sketch the proof, even we cannot go to the very detail of everything, but at least we can share what is the idea of the proof here. First, let D denote to the inverse limit. For each y in y, for each y in 0, 1, closed interval 0, 1, pre-image is either one of the following interval, is one of the following intervals, and all of them are trivial shape. So inverse limit is a trivial shape. The theorem is on this paper. We know that first, the inverse limit is a trivial shape now. And being all factor spaces of F are locally connected, because we have a factor space 0, 1 at least, and graph factor spaces are dendrite at least, and graph is be locally connected, and pre-image of every point be a continuum, leads that the inverse limit D is a locally connected continuum. And from the theorem is and since we do have A union B union C union singleton A are distinct element of this set are distinct. It's easy to see that graph of the composition of F is one-dimensional. So by Ingram theorem, the theorem is here. So we know that the dimension of the inverse limit is one dimension. So the inverse limit is a one dimension. So we just proved that D, the inverse limit, is a dendrite because it is one dimensional locally connected trivial shape continuum. So it remains to prove that D is homeomorphic to G3. To do this, we have to show that all ramification points in D are of order 3 and the set of endpoints are Cantor. The set of endpoints is a Cantor set. To show that, to describe ordinary ramification point in the inverse limit. So it's not hard to see that all ramification point in the inverse limit is in this way. So ordinary point in the inverse limit is of the form. It is, we prove it in the paper. And all ramification point in the inverse limit have this form. Because it's in the intersection of two segments, E1 and E2, when T and T prime are free variable in one of the following interval. So since we know that all ramification points are in the intersection of two line segments, and to show that it is of order 3 exactly, we have several cases. I'm not going to the detail of this, but it depends on where are value TR and TR minus 1 in ABC in one of these guys. So we prove it that in each case, such a ramification point is in the intersection of the endpoint of one of the following line and the intersection of an ordinary point of the other and vice versa. So we have several cases. But the idea of the proof is like this. The remaining part that we prove that all elements in in the or element in the set of endpoints R of the form. So we prove that such set is homeomorphic to the Cantor set by proving that such set is closed, perfect, and totally disconnected. This was our first main theorem of this work. The second main theorem is kind of generalization of this, but the proof is a little bit, we need to be a little bit more careful. So when AI and BI, I be in the set of natural number, be a finite subset of 0, 1, such that union of AI and union of BI is a finite set and with an empty intersection. And let gamma be a set of alpha 1 up to alpha L, be a subset of 0, 1, such that the gamma intersection union of AI and BI be empty. And let Fi be defined like we define F in the previous theorem here, we call that. So when Fi be Fai Bi gamma I, like this, when instead of pick A, BA, we can, for each bonding function, we can pick another apercemic continuous function, where alpha I in gamma. Then inverse limit is still G3. I'm not going to go to the detail of this proof. So I like to go to the other theorems. Let F capital 3, 4 be defined in the same manner of F, except in we change C, we add an extra points other than 0, 1, C1, C2 up to CL, when CI be an interior point in 0, 1 and not an element of A union B union gamma. So we have the following theorem. Like before, let F be F A B A. So we have the same if F be F3, 4, then the inverse limit is a dendrite. This time contains G3. It's not G3, contains G3 and contains countably infinitely number of ramification points of order 4. And the set of endpoints is in the closure of the set of ramification points of order 4. Of course, it's a subset of a set of ramification point of order 3 as well, but this is kind of clear, but we will do for order 4 here. We just like to sketch the proof here. As previous theorem, the inverse limit is dendrite because we know that pre-image of points are continuum and graph are locally connected, so it's locally connected, and it's trivial shape because pre-image of every point is a trivial shape, and it's one-dimensional, so it's a dendrite, as like before. Since the graph of any function in F sub 3, 4 contains a graph of a function in F, so by our main theorem, the inverse limit contains German dendrite G3, because if all of our function be here, we know that inverse limit is a German dendrite G3. If we have a family of apercemic continuous function, its graph contains a graph here, so at least we have German dendrite G3. So let Ci be an element in C other than 0, 1, and T1, T2 up to Tr minus 1. Sorry, this is the set, is a subset. Consider the pointers T up to Tr minus 1, CIAA. This point, it's easily we can to find two open interval I and J contains A and CI, such that this line doesn't have any intersection point other than the ramification point that we pick it here. Other than Tr minus 1, CI, other than the ramification point that we do have. And P, and from here, such P is a ramification point of order 4 because we can prove it by, like we did have, we have several cases to this, that such P is the interior point of this line and interior point of the other line. So this P is a ramification point of order 4, and we don't have any ramification point in such open interval when T is in a factor, when we have an open interval in the factor spaces here, I and J here, because we have T is in J and T prime is H. So correspond to any CI, we have a ramification point of order 4. And since we have at least countably many CIs here, with finitely many, because we may have this interchange by TIs among here. So we have infinitely countably many ramification point of order 4 in the inverse limit spaces. To show that the set of endpoints is in the closure of the ramification point of order 4, let epsilon be greater than 0 and E be any endpoint. Of course, we prove that endpoints on the inverse limit space have the form. Be any endpoint in the inverse limit space, and B epsilon of E be any open ball around such endpoint with center at E with radius epsilon. It's easy. It's not. There exists in the natural number such that the distance between the ramification point here that we do have and Q. No, sorry, the endpoint that we do have and the ramification point of order 4. We can go too far until, because the distance, the metric that we do have, it's xi minus yi over 2, the summation of this guy. So we can easily find Q such that the distance between ramification point of order 4 and such endpoint be less than epsilon. So it means that Q is in the such ball. So for any ball around the endpoint, we can find a ramification point of order 4 in such ball. So we just show that the set of endpoint is in the closure of the ramification point of order 4. The last theorem, if we just pick one or even more, because finitely many F1 or F2, or let me say F1, if F1 be in the family of F3, 4, and for I greater than 1, if I greater than 1, if I be in the family of F that we already defined before, then inverse limit space is a dendrite and contains G3 and contains only finitely many ramification point of order 4. And the set of endpoints is in the closure of the ramification points of, is in the closure of the ramification point of order 3, of course. We don't have order 4, okay. So, and the proof is, this is kind of similar spreadsheet. That's why we name it as a corollary of the previous theorem, but we missed to change it to the corollary. And which is the end of our work here. And thank you. Thank you for being with me.
Thank you, Farouk.
Thank you.
¿Hay alguna pregunta para el ponente? Is there any question? I have a question. Sorry. Is there a family of US upper semi-continuous function F, such that the inverse limit is the dendrite G4?
Actually, if we have when we pick 0, 1 as a close interval, I haven't find it. I don't think. Actually, I even didn't find one other than all factor spaces G4 and pick an identity on it. Other than this,
Okay.
trivial one, I haven't seen with the same bonding function, and even with different bonding function, I haven't seen anything homeomorphic to G4.
Okay. Okay. Thank you.
Thank you.
Is there any question? ¿Hay preguntas? Ok. Parece que no hay preguntas. Okay. We finish this session. Thank you, Professor Farouk, by accepting our invitation.
Thank you.
And
thank you for listening. Thank you.
Thank you. See you.
See you. Thank you. Have a good evening. Bye.
Thank you.